Hello everybody and welcome to Blockchain Expert. In this video, I'll be talking about blockchain security and some concerns that we may have with different aspects of the blockchain. So I actually want to begin by just going through a few potential problems that could occur when you have something like a blockchain network and when you're trying to keep track of different transactions. So let's go through those. I'll spend a minute or two on each, and then I will talk about how some of the things we've already looked at actually kind of avoid that issue for us and add to the blockchain security. So the first thing that we should be a bit concerned about when we're talking about any type of ledger, specifically a digital ledger, is double spending. Now, double spending occurs when someone is able to spend the same coin or the same amount of money multiple times. Now, if we're dealing with a cash transaction where we actually have, say, a dollar bill, well, if I hand this to someone physically, then of course I can't double spend it because they now have the bill in their hand, right? I've given it to them and I'm not able to spend it again because it's physically in a different place. However, when we're dealing with any kind of digital ledger, whether it be a decentralized ledger like a blockchain network, or even just the ledger that a bank is holding, we have to be very careful with double spending. We can't allow someone to try to spend this same $1 multiple times, or to say, spend this $1 and then reverse that transaction back somehow, allowing them to have access to the same dollar, but having already paid for a product or a service or whatever that may be. So how do we avoid double spending? Well, we avoid double spending by essentially keeping a history of every single transaction that's occurred on the blockchain and proving that we have sufficient balance to be able to send money. So of course, we already saw this when we talked about transactions and how you need to feed inputs to your transactions that prove that you have sufficient balance. Now, by doing that, you're saying, okay, I do actually have this money. These are the transactions that gave me this amount. But even with that in mind, someone could theoretically try to use the same inputs to a transaction multiple times. Now, if they were to do that, we would be able to go back into the blockchain history and see that they have used these same inputs before and not allow them to use that input again. And that would be how we would kind of fix that problem. But double spending is a large problem when we're talking about digital ledgers. We really need to make sure that someone cannot spend the same amount of money multiple times and that they can't, say, spend the money and then reverse that transaction back or delete it from the blockchain. So what I mean by that is maybe we have a block where there's a transaction where A sends B 1 Bitcoin. Now this gets added into the blockchain. So let's just add another block here and add it on. And as blocks continue, technically, if we didn't have this blockchain security, what could happen is someone could come into this block and just delete this transaction. Now, if they delete that transaction and they are user A here, that would theoretically give them access to this 1 Bitcoin another time, because then they would be able to send this again and again and again and again. And we would be essentially creating money out of thin air and double spending, which of course is something we want to avoid. So that's double spending. Not much more to say there. Now we'll move on to the next topic. So the next problem or concern that we may have with the blockchain has to do with order. So remember I told you back in one of the previous videos, the blockchains are chronologically ordered. Now that is true for the blocks and when blocks are created, but that's not necessarily true for all of the transactions. So as we should recall here, when we have our blockchain, we have our transaction pool, and this transaction pool contains all of the unconfirmed transactions. So there's a bunch of transactions inside of here, and they can be submitted pretty well at random times, right? And there's usually going to be tens of thousands, maybe hundreds of thousands of transactions in this pool waiting to be picked up by our miners, which again will just be kind of these blocks over here that I will label as miners. Now, these miners are not picking transactions based on the order in which they're submitted. They're picking transactions based on the transaction fee that's provided or some other incentive, but it's not strictly based on the order in which these transactions were submitted. So these miners will assemble a block with a series of transactions, then submit that block to the blockchain, but that block is not going to have all of the transactions ordered in the order in which they were created when they were submitted to this pool. So transactions don't really stay in a chronological order. That's the first thing to understand here. Now, the reason that can be slightly problematic is because that means that I could theoretically submit multiple of the exact same transaction or of different transactions that use, say, the same input to my transaction pool, and there could be problems when I'm trying to add those onto the blockchain. So let's say I submit a bunch of these green transactions. Now, maybe one of these green transactions gets picked up, and let's say it gets added to the most recent block on the blockchain. Well, if I'm using the same inputs to, say, this other green transaction as I was to this one, when another miner goes and tries to create another block that has my second green transaction on it, it needs to know that I can't do this transaction because of the fact that I've already used the same inputs or I've already done that same transaction. It's already on the blockchain. So this is handled by the blockchain, and it's a pretty complicated way of doing that, which we're going to talk about in the proof of work and proof of stake section. However, just understand that this order is taken care of and dealt with by the blockchain. So even though my transactions are not in chronological order, when my transaction is picked up and added to the blockchain, it's written there permanently. And now if I try to do this other transaction, the blockchain will be able to see that the inputs I'm passing to this are not valid because they've already been used, and it would reject my transaction. It would send it back and say, this is invalid. You can't do this. So it's something to consider because theoretically, again, I can try to submit 3 transactions, and the order in which those transactions are going to be added to the blockchain is based on the fee that I pass and a bunch of other factors, a little bit of randomness as well. So I can't really predict that this transaction is going to happen faster than this other transaction. And again, it's just something I kind of wanted to bring up and briefly talk about. I know I didn't necessarily describe exactly how the order is fixed here, but I want you to know that based on the way that blocks are created and transactions are verified, it would be next to impossible for you to submit, say, 2 of the exact same transactions and have those added to 2 separate blocks. One of your transactions would be rejected once the other one is actually picked up and added to the blockchain. So with that said, let's clear the screen here and let's move on to the next concern. So the next problem here to discuss has to do with balance, specifically having sufficient balance to send funds. Now I'll talk about this briefly because we've already kind of looked at how this works, but this is the main reason why you need to provide transaction inputs to your transaction. You are proving to the blockchain with these transactions, and let's just fix this arrow here, that you have sufficient balance to create the transaction that you're trying to send out to however many people with whatever the amount is. So let's say you're trying to send 6 Bitcoin. Again, we know that the sum of the values received from these transactions needs to be greater than the 6 Bitcoin, and then you would just define what you want and change back as another transaction. So the reason you do this, though, is because, of course, yeah, you're providing the proof that you have the funds, but if you weren't to do this, what the blockchain would have to do is they would have to look through every single block, starting from the origin block, and essentially track how much money is currently in your account by going through a history of almost all of the different transactions. Because if you don't provide any proof and you just try to send, say, 6 Bitcoin, so that's the content of your transaction, now the blockchain or the miner specifically need to determine if you actually do have 6 Bitcoin in your account. Whereas by providing your inputs, now all that needs to be done is to see if these inputs have been used before. If they haven't been used before, then you're fine. And if they're valid and you are actually the recipient of these, then you're okay to send your 6 Bitcoin. So that's kind of the basics of how that works. Of course, it's a little bit more complicated than that, but I just wanted to describe kind of this issue with balance and determining the balances of specific accounts at specific times. So the next risk or concern to go through here with blockchain networks is exploited code. Now, I'm sure many of us here are programmers, so we're probably familiar with the fact that we are not perfect and oftentimes make mistakes when writing code, and even people that create large blockchain networks or coins do that as well. So that is always a potential problem, that the code that's written, the actual source code for the blockchain network, can have vulnerabilities in it, there can be problems, and people can exploit that, and they can cause damage to the blockchain network, they can perform fraudulent transactions, all kinds of things can go wrong when you have exploited code. Now, there is ways to avoid this. A lot of large blockchain networks have, thousands of people working on them. They have security audits. It's relatively safe. People know that the source code is fine and that it's not going to be exploited. But on smaller coins or smaller blockchain networks, this is definitely a massive risk. And there's lots of examples in the past of coins or of blockchain networks being exploited because of poorly written code. So just wanted to mention that, another risk or kind of security concern with blockchain networks. So now we're going to move on and talk about probably the most popular, most famous type of blockchain security breach, and that is the 51% attack. Now, the 51% attack occurs when some entity is able to control over 50% of a blockchain network. Now, specifically, they would be controlling the nodes or the validators/miners on that network. Now, again, this is going to make a ton of sense because we haven't done proof of work or proof of stake yet. But the idea behind this attack is that if you are able to control over 50% of the entire network, you are able to essentially do whatever you want on that blockchain network. Now, the reason that's the case is because all of these networks have consensus algorithms in place that allow people to determine, based on consensus, whether or not a transaction or block is valid. So if you were to control 50% of the network, so let's just draw out, say, 5 nodes or validators here. If you controlled 3 of these 5 nodes, if there was to be a problem or a dispute with any of the blocks or transactions data, then what you would do with your 3 blocks is you would just say, nope, that's fine, that's completely valid. And even if these 2 other nodes or other validators on the network were saying, no, this is a fraudulent transaction, we can't let it through, etc., it wouldn't matter because you would have control. You would have consensus because you controlled over 50% of the blockchain network. So that is really the basic premise here of the 51% attack. This has happened to many blockchain networks in the past, where especially if they're very small networks, someone is able to gain control of enough compute power or enough validators, whatever it may be, depending on the network, where they can then essentially control the entire network and submit any type of transactions or data that they want because they always have consensus. So hopefully that makes a little bit of sense, but this is something that should be considered and obviously should try to be avoided if possible. But on smaller networks, it is something that is just hard to avoid. If you only have a few hundred people or 1,000 people using your network, then it's pretty easy to gain control over half of that network. Whereas when we talk about something like Bitcoin or Ethereum or these massive blockchain networks, because of the decentralization and the distribution of the ledgers that they have, it's very unlikely and very difficult to control 51% of that network. It's never happened with Bitcoin or Ethereum or any of the most popular coins to date, but it is something that always has to be considered, and that a lot of coins will implement kind of interesting security mechanisms to try to avoid a 51% attack. Anyways, that is pretty much all I had for you for the 51% attack and actually for this video. Again, I know that not all of this will be crystal clear because we haven't gotten into the more complex aspects of the blockchain and how the consensus algorithms work, like proof of work and proof of stake, but we will talk about those and you will see why those are kind of in place to avoid some of the issues that I just talked about in this video. So with that said, I'm going to wrap it up here. I hope this was helpful, and I look forward to seeing you in another Blockchain Expert video.